Hey guys, today's lesson is on implicit differentiation. Up until now, all the derivatives that we have taken before have been in the form of y equals or f of x equals. Those are explicitly defined. Now we're going to look at equations that are defined implicitly, which have x's and y's on the same side of the equation. I've written an example for you on the upper left. It's the equation of a circle. X squared plus y squared equals 4. We've seen this before in Algebra 2 when we studied conic sections, but we're going to learn right now how to take the derivative of such implicitly defined equations. We'll start with example A. Find the derivative with respect to x of the expression x cubed. If there's agreement in this x on the bottom and the variable in the expression, then it's just very, very simple. It's going to be just like we've always taken a derivative before. We're going to use the power rule. So the derivative here is going to be 3x squared. And that's it. So if these are in agreement, same as it always has been. When we go to example B, however, these variables disagree. And if they disagree, that's sort of a trigger that you're going to need to use implicit differentiation. Always bear in mind that we're taking the derivative with respect to this variable on the bottom, and in this case it's x. So we're taking the derivative with respect to x of the expression y cubed. So to do this, we're going to use the power rule, 3y squared, but then we're going to have to use the chain rule and take the derivative of this expression with respect to x. So that's just going to simply be dy dx. And I know it's a little funny to have that in your answer, but for now it's going to be fine. Let's take a look at another example. I think the more that we see, you'll become more comfortable with the notation. Here we have the sum of two expressions. The first expression is in x, it agrees, so that's going to be good. The second expression is in terms of y, so this is going to require implicit differentiation. The derivative with respect to x of the expression x is just 1. The derivative with respect to x of the expression 3y is 3. But then we need to use the chain rule on this, and we end up getting dy dx. So again, that dy dx creeps into our answer. For our final example, we have a product. The first factor is in terms of x, so that's fine. And then the second factor is in terms of y, so we're going to need to use the implicit differentiation. And maybe this doesn't deserve the sad face, maybe it's just not that big of a deal. So we're going to set it up old school for organizational purposes. The first factor is x. Its derivative is 1. The second factor is y squared. Its derivative is 2y. But remember, we're doing this with respect to x, so this needs a dy dx after it. When you do the product rule, it's going to be the first times the derivative of the second plus the second times the derivative of the first. So what we're going to end up here with is x times 2y dy dx plus y squared times 1. And we'll just clean this up a little bit. 2x y dy dx plus y squared. So the answers here, they look a little funny. Some of them have dy dx in it, some of them have y's in it. But that makes sense because the original implicit equation had x's and y's in it. So it's only to be expected that there's going to be y's in your answer as well. In our next example, you're asked to find the derivative of an implicitly defined equation. I've written a procedure off to the side of what you should expect along the way. We're going to start by differentiating both sides with respect to x. When that's done, we're going to have what I call a dy dx party, which means bring all terms that have dy dx to one side and all things without a dy dx to the other side. The dy dx is sort of like your invitation, and you can only come to the party if you have one. Then we're going to factor out the dy dx from whichever side you're having the party on, and then you're going to isolate by dividing away everything else. So to start this problem, we're going to look at each term separately like it's its own little mini problem. So we're going to start with 3y squared dy dx. And then we move to the second term, 2y dy dx. Third term, minus 5 dy dx. Fourth term, now notice we're differentiating with respect to x, and this is purely an x, so this is just going to be old school. We don't need a dy dx there. And then this constant, the derivative of a constant, is just 0. So step 1 has been completed. We've differentiated both sides with respect to x. The next thing we're going to do is have this dy dx party. 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. So I move this term to the other side because it does not have a dy dx. Now these three terms that do have the dy dx, I'm going to factor that out. So we've accomplished step number 2, and now we're going to go to step 3, which is factor out the dy dx. So I'm going to take out dy dx because it's on all the terms on this left-hand side. And then what I'm left with is 3y squared plus 2y minus 5, and that equals 2x. And our last step is to isolate dy dx, and we're going to do that by dividing away everything else. So dy dx, also known as the derivative, is equal to 2x all over 3y squared plus 2y minus 5. So it looks a little scary. A lot of algebra going on here, a lot of calculus going on. But if you're neat and you're organized and you go slow enough that you can be conscious of any careless errors that you might make, it's not so bad. Here's a very typical calculus question asking you to find the slope of the tangent line. But this time, in order to do that, we're going to need to implicitly differentiate. So the function that they give us is x squared plus 4y squared equals 4. Taking each term one at a time, our first derivative is 2x. Our second derivative is going to be 8y followed by dy dx. Don't forget we're chaining any expression that's not in x. And the derivative of a constant is 0. So we're just taking each term one at a time and finding the respective derivatives with respect to x. Now we're going to have a dy dx party. So we're going to say 8y dy dx is equal to negative 2x. Now we're going to isolate the dy dx by dividing away everything else. And now we get negative 2x over 8y. The negative 2 and the 8 cancel out, or the 2 and the 8 cancel out, leaving us with negative x over 4y. So this is our derivative. This is our equation for the slope of a tangent line at a specific point. Well, they give us the specific point. This is our x, and this is our y. So we're going to plug that in. So we have the opposite of root 2, or negative root 2, which I'm going to make negative root 2 over 1, over 4 times y. Now y is written a little bit weird, but it's negative 1 over root 2. So cleaning this up a little bit, we've got negative root 2 over 1 all over negative 4 over root 2. Now, dividing by a fraction is like multiplying by its reciprocal, so it becomes negative root 2 over 1 times negative root 2 over 4. The product of two negatives is a positive, so we've got 2 over 4, which reduces, of course, to 1/2. 1/2 is the slope of the tangent line at this specified point. This here, our original implicit equation, was that of a conic section. Does anyone know which conic it is? So for those students who are actually curious to know what conic that was, I thought I would take 2 seconds and discuss that, and maybe even graph it and see if 1/2 as the slope of the tangent line is a reasonable answer. Okay, so what we're going to do here is divide everything through by 4. Most conic sections are set equal to 1. Most of them are. So this ends up being x squared over 4 plus y squared over 1 is equal to 1. And as some of you may have guessed, this is the equation of an ellipse, the center of which is at 0, 0, and it's oriented horizontally. And I know that because the larger denominator is aligned with the x. So let's draw a sketch of this. Okay, so I'm going to go the square root of 4, 2 units left and right. 1, 2. And I'm going to go the square root of 1 unit up or down. And we know what an ellipse looks like. It's like an oval. So I'm going to draw an oval looking thing like this. Okay, not amazing, but whatever. All right, so the square root of 2, we're going to look at this specific point. The square root of 2 is like 1.4 something, and then we're going to go down negative. So this is the point we're looking at. And I have to draw the tangent line. So let's see if we could do that. Just sort of eyeballing it. That looks like a good tangent line. Now this is positive, and we got an answer when we did this manually. We got an answer of 1/2. That's supposed to be an arrow, not a cross. Let's change that. Okay, so we got a slope of a half doing it manually, and if you look at this, it could just as easily be rise 1, run 2, 1/2. I like it. I think we're good.